Okay, folks, welcome back. Sorry for my being late. I need a helicopter and not a car. Okay. Do you have any questions about what we have seen so far? How was the training in the lab? Not good. But you can bring your portable and work on your portable if you wish, and install directly things on your portable, so you have a working environment that you can use at home as well. You don't need a network, so just bring your portable and install on your portable. It's a Chigwin and it's Eclipse, Ganymede, and it's C and C++ and the GLUT libraries. You can download everything when you're at home and prepare everything and then bring your portable. So don't use this as an excuse for not working. Why not? Well, you have guidelines on the website, and sooner or later, if you want to do something, you have to set up the environment on your own PC. So that's okay. That's okay. You have the guideline. I have seen it. It's over here. Installation guide for Eclipse with Cygwin plus GLUT. That's the one you should need. So if you by chance you happen to be on a workstation on the lab which is not working, you can bring your own PC and follow. I mean, this is the resources we have. Okay. What I'm going to do today is to finish my introduction about, well, basic things of computer graphics, and then we will forge ahead to geometry for computer graphics. Well, we've been talking last time, well, 2 weeks ago already, we've been talking about the pipeline, that we mainly have some stages in the pipeline that every computer graphics engine performs when you want to move from the domain of, well, vectors, which are modeling your scene in a mathematical way, on to rendering, which is transforming that mathematical representation into a raster-based data. This pipeline has different stages. The order of the pipeline and the complexity and exact order or sequence of transformation and operations of each pipeline is up to the specific rendering engine, but more or less the main building blocks of what a graphic pipeline does is transformation, that is moving 3D objects in the scene according to the updated position of the viewer. Then projection, that is reperform a projection from the 3D representation into a 2D space, because this is what we ultimately need, bidimensional projection that we will use to perform a representation of the rendered image on the bidimensional space of your monitor. Then shading, which is perform a calculation of color of each vertex and ultimately of each pixel. And then rasterizing, which is in fact converting all this mathematical information into a raster-based information, so into a real pixel with real color into a specific position. So this is the basic order of the pipeline. Let's delve a little bit more into detail about the problem of viewing. So I told you that we need transformation, that is moving objects, and then that we need a specific operation which is called projection. Why do we need projection? Because we have a scene, and then we have a viewer, but the fact that the viewer ultimately views looks at the scene through a bidimensional area. This is true also for our viewing system. We ultimately project all the scene around us to the back of our eye, in our cornea. And this is the same for a photo camera. Ultimately, this 3D image is projected onto the back of the camera, which hosts a film or a digital sensor, which is bidimensional. So what happens is that you have a projection from a 3D environment into a bidimensional plane. This plane is called the projection plane, and the fact that this projection plane is actually limited in dimension and in space causes the fact that we do not only have a projection, but we also have a clipping that is part of the image fits into the bidimensional projection plane, and part of the image is clipped away, is cut away. Why? Because of the nature of the field of view. You see an example here. We can imagine this projection plane as a window through which the observer observes the scene. This clipping window can move if the observer moves in relation to the object. So, part of the scene can be projected in a specific way, or part of the scene can be clipped away. The fact that the scene or part of the scene is clipped depends not only from the position, from the mutual position of the observer and the scene, but also depends on a specific characteristic or feature of the viewer, which is the depth of field, or conversely, if you want, the field of view that a specific viewer has. This is a characteristic which is related to the optic system of the viewer. If we consider a human viewer with human eyes, just the naked eye of a human person, then more or less the depth of field of a human person cannot be changed. I mean, every one of us has a fixed depth of view and has a fixed field of view related to this depth of view. If we are looking in front of us, we see the scene in front of us up to a certain angle. But we cannot see behind our backs. We need to turn our viewing system in order to bring another part of the scene into our field of view. This is not true for all viewing systems. For example, dogs have eyes a little bit shift to sides, and they have a much ampler field of view in respect of our. Or, for example, we could put in front of our eyes a telescope. This allows us to see things that are very far, but at the same time it narrows our field of view. So we can see things very near, but we don't see as many things as we can with the naked eye. So there is a relationship between the depth of field, how the depth of field is, how far or how near we see things, and the field of view, which is the angle of the pyramid, which is called the frustum, which contains things we can see. You have a small representation here, but it gets better if we draw it together. So let's see if I can make this shift easily. No, this is not. This is it. But then you need it over there as well. Here it is. You can understand better the relationship between the field of view and the depth of field, if you consider the metaphor of the pinhole camera. What's a pinhole camera? Well, it's basically a viewing system which you can imagine made up of a shoebox. A shoebox is a box in which you put shoes. The shoebox has a box with a lid over it that you can easily open. The idea is that you make a very small hole on this side of the shoebox. That's an experiment that probably you did when you were a kid. If you put a very small hole, so small, such one that can be made with a pin. You know what a pin is? Something pricky that makes a very small hole. Such a small hole is called a pinhole because it's a hole made with a pin. Well, I'm sorry, but it's half computer graphics lesson and half English language lesson. So it happens. If you make such a small hole, then imagine that you have an object in front of it, like this. Okay? Light is coming inside the hole and projecting on the bottom of the shoebox over here. So this has to be our projection plane, right? What happens? That light can be modeled as a ray, and the image forms like projecting rays like this. So what you see on the bottom of the box is something which is the inverse of the image you're looking at because of the way the projectors are moving, you see. And the sides, according to the clipping plane, is related ultimately to what? Is related to the depth of field. You see? What's the depth of field? Well, the depth of your shoebox. Or to say it a little bit more technically, the depth of your viewing system. The distance between the hole in which the light enters and the projecting plane. This hole is called the COP, or center of projection, where all the projectors meet. Why the experiment is made with a pinhole? Because if you have a pinhole, you don't have anything, like for example a lens, to influence the direction of the projectors. The only way you have to change the way the projectors behave onto the projection plane is to change the size of the shoebox. This is the only way you have. So for example, if, okay, these are my shoes, then I take another shoebox, the shoebox of my wife's boots. That's much bigger shoebox. Well, the boots are like that. So try to live with a woman and you will understand the problem you have when she starts buying boots. Okay, so that's the shoebox of my wife's boots. The only advantage you have is that you can make such experiments. What happens? Now you have a viewing system with a way bigger depth of field, because my box is longer. So if you take the same object, okay, imagine that it's the same object with the same size, right? What happens to the projectors? that, of course, you are forced. Oh, I need a ruler. Of course, the projector behaves in a different way because the projecting system is changed because you have a much more depth of field. So, what do you see in the projecting plane? You see something like this. Okay, actually you don't see this part. What you see in the projection plane is this part over here, right? So, actually what happens? If you imagine that this is the back of your eye, the feeling that you have is that you see the same thing, but much bigger. It's like you're zooming in, right? You see? It's the same object, but you see it much bigger because it occupies all the area of your projection plane, of your clipping plane, of your viewing plane. Can you imagine it? Can you see it? You can see it, the object gets bigger, right? So, with a longer depth of field, oh Jesus, it's this way. It's zooming. Okay? You zoom in. If you wanted to see the object smaller, what you would have to do is to use the shoebox of your son, if you have one, of your small son. Then you get a much smaller shoebox. Okay, you can do your experiment yourself. And the result is that you get a much smaller image because you're narrowing your depth of field. I don't have space here, but you can draw a smaller shoebox, make the same object, project it, and you will see that you will get a smaller one. Getting a smaller one means that you see it more distant because your clipping or viewing area is the same. So you're actually zooming out when you're taking a smaller depth of field. First consideration. Second consideration, your depth of field is obviously related to the angle here, which is called the field of view, which represents the quantity, the area of things you can see. As you can see, this angle here, over here, is much narrower. So the longer is the depth of field, the narrower is the field of view, the nearer you have the impression to be to the object. This is how the optic systems work. What is the improvement on modern optical system against getting shoeboxes? Is that you keep the same shoebox, because when you have a photo camera, you are not getting the photo camera, deeper or thinner. This is how old cameras work. Have you ever seen in some movies those cameras that were built like this, right? Why they were built like this? Because you could easily change your depth of field by just pushing and extending the camera. Why would you want to do that? Because you wanted to photograph things nearer or farther away. Now we use a much smarter system, which is keeping the sides of our viewing system fixed, but virtually changing it by changing how the projector focuses on the clipping area with the lens. This measure, which is the depth of the viewing system, is actually moved to the lens. So we say that you have an 18 millimeters or a 50 millimeters or 100 millimeters lens. Have you ever heard about this? You classify the capacity of your lens in millimeters. For example, if you buy a reflex camera, usually the standard lens that goes with your camera is an 1855. What does it mean? It means that you can virtually simulate, by changing your lens, a shoebox which ranges from 18 millimeters up to 55 millimeters in depth. As a reference, you can say that the average depth of field that we have with the human eye is a depth of field that can be reproduced with a box of 50 millimeters. So if you use a lens of 18 millimeters, what happens? You have a very short depth of field, which means that you can have a wider angle than usual, but things tend to be farther away, smaller. This is the lens you use when you're going to photograph a marriage party. You know what a marriage party is? When there is somebody's marriage, and you invite 100 people, and then you're obliged to do one photograph in which all the people is in. That's dumb, because 100 people, and the photograph is what is going to show. It's going to show so many small, but is it, and after 20 years, is it you? Yes, maybe, but I'm not sure. Okay? Why? Because it's 100 people. To make them fit in the field of view, the only chance you have is to make the people very small. So you have the marriage party effect. To get that, you need a very short depth of field, a very high field of view, meaning that every object is very small. On the contrary, you have to photograph Monica Bellucci sunbathing on a beach in, I don't know where, in France. Okay? Of course, you are not allowed to photograph Monica Bellucci with a standard lens, because that would imply that you are near Monica Bellucci, which is, you are engineers at Politecnico, which means that you will never get near Monica Bellucci. So what you need to do, you need a 100 or 200 millimeters lens. Being an engineer at Politecnico, probably you are on a tree, 1 kilometer far from Monica Bellucci, using your lens. So you can get very fine details of her, the eyes probably, with a long lens. That kind of lens, or that kind of depth of field, ranges, I don't know, if you are on a tree, you probably need a 250 millimeters. It's those kind of canons that you see on with professional photographers or paparazzis use sometimes. They are so heavy that they need 2 tripods. One for the photo camera and one for the lens. They're really heavy. Which means you can't be on the tree anyhow, so that gets a problem. But on the contrary, what you see is that you can photograph the detail, I don't know, the eyes. They can be very near. You can do a very good zoom, only of that. And why only that? Because your field of view is very narrow. Okay? So you concentrate, you focus on a specific detail. So that's field of view. And that's the relationship between depth of view and field of view. All of this has to do with projection. When you're doing projection, you see, and RGB. When you're doing projection, you take into account what are the features of my viewer, which is what is the depth of field of my viewer. This is one. As I told you, this is important because it determines if you are seeing just one specific part of your image or you can see a wider area. And you need to know if you are projecting using a perspective projection or you're projecting using a parallel projection. This is something which is a little bit more, well, it's more difficult to make a parallel on our everyday life. Because in our viewing system, we do not have the possibility to choose between a perspective projection and a parallel projection. we work as a pinhole camera, which means projectors are never parallel. You have seen in my drawing, my projectors are always going through one single point, which is the center of projection. This is the only viewing system we have in nature. It's called a perspective projection. A perspective projection means that all projections sooner or later meet in one single point, which is the center of projection, which means that projections are never parallel. This is, by the way, what gives us the sense of depth. Why? It's always related to the depth of field. Because if you move farther, or you move nearer, or you change the depth of field, then the size of the object that you are viewing changes and gives you the idea of depth. When you're going nearer, you see things bigger because your projection system changes, and you see, I'm very near, I'm very far. I can feel the distance, I can see the distance. But this is not the only possible system for creating projection. The other system is, I do not want projectors to meet in a point. Or to see differently, my projectors meet in a point which is actually to the infinite. Oh, welcome. I know this beamer. This is the guy which makes purple things. Okay, anyhow. I'm afraid that in a few minutes it will go out. But anyhow, you see, in this example, you could say that the projectors meet, but not in a point which is indefinite. They meet in the infinite. And another way to say this is that they are parallel. With a parallel projection, you obtain a completely different image on the projecting plane. And with this image, no matter if you move nearer or you move farther your center of projection, since you're set moving nearer than infinite, it means that your center of projection is always in the infinite. So even if your viewer has an orthogonal or parallel projection, even if you move nearer or if you move farther away, the size of your projection does not change. So you lose the impression of depth. These are the two basic projections that you can make. OpenGL, you have probably seen it already with Raffaella, gives you a powerful viewing system with the possibility to plot 3D coordinates into a viewing window. When you're opening the viewing window, you have to specify which kind of projection you want from the 3D coordinates which are in OpenGL's memory into the viewing window. Do you want it to be projected in parallel projection, or do you want them to be projected in orthogonal projection? This is a choice you have to make. If you choose ortho, then be aware that with ortho you cannot get perspective effects. You cannot get that effect of things getting nearer or farther. But you got a kind of visualization which could be useful, for example, when you're making architectural visualization and you need floor plans or technical drawings of objects. Then the kind of projection you make, you don't want them to change in size. You want them to be precise and to be useful to take measurements on them. So, I'm not saying that perspective projection is useful and parallel projection is not useful. They're both useful, but for different purposes. So this is, I wrote there in this slide. Then these are the two main areas, perspective and parallel. Then you have different variations for each one. For example, there are different kinds of perspective projection, and you can differentiate them according to how many vanishing points you are using for your projection. These are three kinds of perspective projections in which the projectors are not parallel, but the projectors are disposed in a way that you can identify into the image 1, 2, or 3 vanishing point. What is a vanishing point? It is a point in which one main direction converges. You have basically 3 main directions. One for each one of the 3-dimensional directions of space. Let's see. Oh, I don't have a pen here. Right. So I cannot pull my usual prank. But maybe I have it here. Oh, I cannot draw on it. Shit. That sucks. No, I can't. Okay, we'll do it like this. For example, here you have only one vanishing point. Do you see it? Because in this direction, everything is parallel. In this direction, the lines are parallel, you see? But in this direction, which is the z-axis, the lines meet behind the temple. Can you imagine this? That's one vanishing point. Let's see if we can do something like this. These ones are parallel. These ones are parallel. But these are meeting in one vanishing point. You see? Here you have how many vanishing points? You have 2. Because here you have parallel lines. But here you have one vanishing point over here. And then you have one vanishing point over here. No. Over here. Here. And here you have 3 vanishing points. One over here. One over here. And one over here. So as you can clearly see from this picture, 3 vanishing points. Good. Also, parallel projection have 2 basic types, orthogonal and oblique. Orthogonal parallel projection are projections in which the projectors are orthogonal to the viewing plane. Oblique parallel projection are projections in which the projectors are not orthogonal to the viewing plane. So, this one is an orthogonal parallel projection, if the projectors were somehow made like this, I'm sorry, it's not very parallel. But imagine that they are parallel. And the plane is here. Then you see, this is the orthogonal. These are not orthogonal anymore. So this is a parallel projection, but not an orthogonal parallel projection. This is an oblique parallel projection. The effect is quite rare. I mean, this kind of projection is rarely used. The only way to obtain it with modern viewing system is to use bellow camera. A bellow camera is that camera I drew before that you can make it shorter or make it longer. And the idea with that bellow camera is that you cannot not only change the depth of field, so its depth by moving the bellow, but you can also shift the planes by shifting the clipping plane of the camera like this, by moving a little bit forward one side and a little bit backward the other side. Then you could obtain some strange kind of projection. But that, of course, then it wouldn't be a parallel projection, but an oblique parallel projection, but just to give you the idea. Okay, this I don't need, this I don't need, this I need. Okay, so this is a few basic about projections. Then the viewing volume. Now we know the meaning of depth of field, and we know that the depth of field is related to the field of view, and everything is centered on the concept of the COP, or center of projection. If you're considering a perspective projection, then the viewing volume, that is the volume that represents the area, well, the volume in which are contained all the things you see, the shape of this viewing volume is called a frustum. What's a frustum? A frustum is like a pyramid, but without the top, which is cut off. So this is the frustum over here. So you see, this is the complete pyramid, but you're not considering all the pyramid, but just the beginning of it, the base of it, without the top. This area in gray over here is called the frustum. And because this frustum represents the area in which are contained all the things that your viewing system can see, this is called the viewing frustum. To be more precise, in your viewing plane, you will see projected with a perspective projection all objects which do fall inside this frustum. The frustum is calculated by the distance which occurs between the viewing plane and the center of projection. This identifies the pyramid. The volume itself is further limited by two planes, which are called the front clipping plane, which is this one, and the back clipping plane, which is this one. Every object which lays in front of the front clipping plane will not be seen. Every object which lies behind the back clipping plane will not be seen as well. We will render only things which lay inside the viewing frustum, as defined by the size given by the mutual position of the viewing plane and center of projection, and the top and the bottom given by the front clipping plane and the back clipping plane. This frustum is important, and in the end we will know the equations of the planes, because this is the base we use to decide if certain objects in the scene are to be rendered or are to be discarded. This is the base volume that we will use. Okay, this is one basic core concept that we will see, the viewing frustum. The other core concept that we will see is the concept of polygon. Everything that we consider in computer graphics is modeled using vertices. Vertices, well, a vertex is a point in a 3D space having, well, let's say for the moment 3 coordinates, even if this is not actually true, but let's say x, y, z for the sake of simplicity for a moment. We join together these vertices 3 by 3 to form triangles. These triangles are called polygons. We use polygons as the base to form more complex surfaces, which are called polygon meshes. These surfaces are used to model objects. Every object you see in computer graphics, even if it appears to be a 3D solid, like for example this, you could say it's a sphere. You could say it's a sphere. Well, actually, it's not a sphere, because you can see that it's an approximation made up of a mesh of triangles. 1. Second, it's not solid because it's hollow. What does it mean hollow? It means that it's not full. It's just a surface with nothing inside, so it's not solid. It's a surface shaped as a sphere, but it's hollow inside. It's just a mesh of polygons. Of course, the finer your polygons are, that is, the smaller your polygons are, the more similar this thing becomes to a sphere. Can you imagine that? It's the same thing like using pixels. If you use big pixels to make a curve, then what you get is not actually a curve, but, well, a series of squares placed, well, in a curved shape. But if you use very small pixel, then you can make a very fine, very nice curve. The same thing with a sphere. Smaller the polygons, the higher the number of polygons you need, but the smoother the shape, the mesh. Why do we use triangles? Do you have any idea? We use triangles because the triangle is the only polygon which we are sure lays on a single plane. If we would use 4 vertices, then we are no longer sure that any 4 vertices could be coplanar, put on the same plane, if you think about it. It's not forgiven that if I take 4 points at random, I can form a polygon with 4 sides which lies on a single plane. Can you imagine it? It can happen that I have something like this. taking 4 points at random, and I am not able to create a coplanar polygon, but I get a curved polygon. Whereas with a triangle, I'm always sure that I can form a polygon lying on the same plane. Can you see? Well, you have to imagine it, but can you see it? Why this is important? Because of the availability of a single normal per polygon. What's a normal? A normal is a vector if this is the polygon, then this polygon lies on one plane, and the normal is a vector which is orthogonal to that plane. In this way, I can say every single polygon that I will use for drawing my mesh can be represented by one normal. So you see, in this representation, this polygon is oriented like this, and this other polygon is a little bit more raised because you can see it's normal. You see? But over here, I have several normals for the same polygon. Here I have always the same normal, everywhere, in every point of the polygon. You see? And the normal is always oriented in the same way. That's cool, because I calculate the normal in one point, that normal is good for the whole polygon. But here, this is not possible. If I calculate the normal here, then in the same polygon but in a different direction, I have a different normal. So I can have many normals for the same polygon. Well, this is, I don't mean it's evil, but for sure it makes things a lot more complicated. So yes, for us engineers, it's evil. So this is much more simpler. We draw everything as a mesh of triangles, and every triangle can be linked to just one normal, which identifies univocally its direction. That's good. That's why we use triangles as polygons and not any other fancy shape. RGB again. And I have to switch it to, I think, PC over here. Right. Okay. So I've given you a little bit of hint about polygons, meshes, normals. That's good. Why do we need normals? Why are we preoccupied with that? Because normals are a very easy way to understand the orientation of each polygon. Why am I interested in the orientation of the polygon? Because the way in which the polygon is oriented affects the way it is shaded. What does it mean shaded? The way, if you want, in which it is colored. So just imagine you have something, and the color you see on this something really depends, of course, from its material, but it also depends from how the light shines on it. Let's make a rough example. You have, I don't know, a red sphere in front of you. No, the sphere, no, it's a blood example. A red sheet in front of you. A sheet of paper, red. And you're looking at it, and you say, ah, it's red. Then, abruptly, all of a sudden, somebody switches the light off. Okay? What color is your sheet? You don't know, because you don't see it. Why? Because there is no light shining on it. So, the condition of light is important to see the color. Then let's say that somebody opens a little bit the door, so very few light enters the room. So you're almost in dark, except for a very few lights. What is the color you see your sheet of paper, you see it gray or gray reddish, but not that nice red as you can see it when you are in full light. Have you ever noticed? When you are almost in the dark, all things lose color. Why? Because there is no light shining on them. If you are in this kind of semi-dark condition, if you start turning the sheet of paper, then you can see that parts of the sheet of paper gets redder and parts gets grayer. That depends on how many light shines on your sheet of paper. So the orientation of your sheet of paper changes the color of it because of the direction in which the lights shine on it. If you don't believe me, well, just go home and try it. Close yourself into your room and make a few experiments with no light, with some light, and you will see that the color you perceive changes with the quantity of light and the direction in which light shines on the paper. How do you determine the direction of the polygon? But why? By looking at its normal. That's why it's important. So we will see, going further ahead with our course, that we will not use not only the normals, but the position of the viewer, the position of the light source, the reflection vector, and so forth. We will calculate 4 or 5 vectors, and by using those vectors, we will be able to use an empirical model to describe the intensity of light in a specific point, and derive the color of that point. With that calculation, we will be able to decide at rasterization stage which color to use for which pixel. That is called the shading model. That's good. So we have to take into account the material of the object, the orientation of the object, the position and the nature of the light source. But you have to consider a final thing, which is the illumination model. The illumination model considers the way light interacts not only with a single object, but taking into account the fact that the object is immersed into an environment, in an environment. Of course, this is the way light behaves in nature. We see reflections, we see shadows, we see transparent objects, and through the transparent objects we see other objects. This is the reality, our everyday reality. To reproduce such complexity in computer systems means that our illumination model, every time that computes the color of a single vertex into a single object, has to take into account not only that object, but also all the other objects in the scene. That's called a global illumination model. Why global? Because to determine the color and shade of each object, it does not only suffice to consider that object, but you also have to consider all the objects around. So you need to consider the object immersed into its global environment. Of course, it requires a lot of calculation, a lot of considerations, because you can have a lot of objects out there around the other object, and you have to consider all of them and how the light shines and refracts from your object into the other object and back into the object that you are considering. So there is a lot of ray following to do. Ultimately, this is possible, but requires a lot of processing power and time. So you trade time for quality, for a realistic result. In the opposite, if you don't care much about realistic results, but you need processing to be done fast, in real time, then what you could do is local rendering, using a local illumination model. In a local illumination model, what you do is actually you consider every object as if it were the only object in the scene in that moment, which means you don't have no reflections, no shadows, no transparency, or if you have transparency, then you can't see what are the objects behind through that object. Why? Because you're rendering every object as a single entity in the scene. So you cannot calculate shadows or reflection in that pass. Of course, this is not realistic. It doesn't give you the sense of reality, but it gives you speed. It's the example that we did the first week when we met, if you remember. The difference between the project which allowed you, well, you remember the Santa Tecla roller coaster, right? Well, you could go around in your roller coaster, you didn't have control, but you could see reflections in the water, shadows from the fire on the pillars, and so forth. You didn't have control because the system is not able to recompute in real time the change you perform on the scene while you're moving around on your own. But, trading that, you have all pre-processing, pre-rendering, and you have a realistic scene. In the Duomo example, you didn't have shadows, you didn't have reflections, but you could move around by yourself. And every time you moved around, the system was able to calculate in real time the new scene. So you trade interaction for quality, for results. So both illumination models are useful. Both illumination models exist in the realm of computer graphics. Let's look a little bit more. So this is light and matter. That's okay. What are the possible rendering methods? I've been talking about light shining on objects, making shadows, and so on. What is the approach that we use in computer graphics to perform this calculation about lighting? There are basically two rendering methods that are used in global illumination model. You are probably aware of them. You have probably heard them already. One is the ray tracing method, also called recursive backward ray tracing. Did you ever hear ray tracing around? Probably yes. The other method is radiosity, or radiosity rendering, over here. Well, what's the difference? The ray tracing approach is based on optical geometry. In optical geometry, light is modeled as a ray. This ray has the property of going through objects and being reflected or refracted, which is deviated through a transparent object, or absorbed. So when you're using a ray tracing approach, you are actually basing yourself on the model of optical geometry. Everything is a ray, and this ray can be reflected or refracted or absorbed. Each ray carries a quantity of energy, which is its light intensity. So by using this model, you can actually perform very precise calculations and obtain good results. The advantage is that the calculation is really geometrical based, vector based. So it's very easy to carry, it's very easy to implement and program. The disadvantage is that with complex environments, the number of vectors you need tend to explode very rapidly. So you very soon have a lot of vectors, a lot of rays to follow, a lot of computing power and memory that you need. What is the idea? that you actually cast for each pixel in your raster. You cast a ray from the center of projection to the scene and check if this cast ray can reach a light source. Well, now you understand why it's called backward ray tracing. It's called backward because it does the opposite than what really happens in nature. In nature, light starts from the light source, hits one object, gets reflected from one object, part of the light is absorbed, part of the light is reflected, and arrives into the center of projection, which is my viewer. This quantity of light which arrives into my viewer contributes to the color I see. This is why when I close myself in a dark room, I don't see anything. Why? Because there is no ray coming from any light source arriving in my center of projection, which is my eye. As soon as there is a little bit of light, that is rays, which start coming inside my eye, then I start seeing things. And the more light arrives in my eye, the more color I see. No light, no color. Very few lights, almost no color, gray. A lot of light, so your girlfriend, clad in a beautiful, small red dress, laughing in the sunshine. The red of her dress is very red, and you will remember that red forever. Why? Because there is the light of the sun shining at full power on her red dress, making that red unforgettable. But then, after the laughing and the sunshine, the girlfriend goes in the dark room. And then you don't see the red dress anymore, because she's in the dark room. And the dark room doesn't allow you to see how red is her dress anymore. So you see? No light, no color. Well, it seems trivial, but you have to start thinking in that terms. The quantity of color I see corresponds of the quantity of energy which survives after a few reflections. At every reflection, part of the energy is absorbed, part of the energy survives and gets reflected. The energy that survives after every reflection, in the end, hits my eye. That quantity of energy which survives determines the color that I see in that specific area of my raster. This is how ray tracing basically works. By tracing in the opposite direction the rays which represent light intensity. This works good as long as I have a small number of rays in my scene. But in nature, light interacts with matter in different ways. I can have specular surfaces, I can have diffuse surfaces, I can have transparent surfaces. These three categories of surfaces are different because they are three different materials which behave differently with ray of lights. In an ideally specular surface, all the incoming light is completely reflected with no absorption, and the reflected ray is a single one in one single direction. Then I can have a little bit less ideal specular surface, in a little bit less ideal specular surface, instead of having just one ray which is reflected, I have a lot of rays reflected, but all these rays are contained in a very small angle. This is what we call mirror, a real mirror. A mirror has the property of reflecting the incoming rays, well, ideally as just one ray, but in reality as a series of rays, but all of them contained in a very small solid angle. This is what gives you the illusion of reflections. On the contrary, you have diffuse surfaces. Diffuse surfaces scatter around light in all directions. An ideally diffuse surface scatter around light homogeneously in all directions, which means that there is no preferential direction that the light takes. It is homogeneously distributed. This is, for example, the surface of a rubber ball, a ball made of rubber. You can see, if you shine light on a ball made of rubber, then you can see that light distributes on the ball, making it, well, luminous more or less everywhere. The light gets distributed on all the surface of the ball, of the sphere. But instead of having a rubber ball, if you have a crystal ball or a glass ball, a ball made of glass, then you can see that if you shine a light on it, all the light kind of gets concentrated on one small spot on the top. Can you imagine that? That's because the light gets reflected in a very small solid angle. That's a very specular material. Then you have a third category, which is transparent surfaces. So ideal transparent surfaces let all the energy which is incoming on the surface cross the surface. The only thing it does is that deviates the direction of the incoming light. So you have an effect which is called refraction. So this complicates things when you're considering the approach of ray tracing on objects which are made of different materials. Ray tracing works very well with objects which are made mainly of specular materials. Why? Because then you can approximate by just saying all these objects are specular, then all incoming rays have the effect that only one reflected ray is generated. You see? This working hypothesis implies that all the objects in your scene are specular. This is why you can recognize very well when an image is rendered using ray tracing, because it seems that all objects are like polished by your own. Your own has passed and polished everything. Everything is bright, brilliant, like if it is made of marble or of glass. Have you ever seen a ray traced image? Everything is very shiny. Why is that? Because the assumption is that every reflection is mostly made by one ray or by a very few rays. And this implies that the appearance of the object is specular, very shiny. If you wanted to simulate a diffuse appearance using ray tracing, then the tree of your rays would explode, because many rays would form at every intersections. So you would have a lot of rays here, a lot of rays here, and you would have a lot of ray combinations to follow. Your ray tree, the tree of your rays to follow, would explode. You will have a lot of rays. which would make this kind of approach unsuitable. And in fact, this kind of approach is unsuitable for diffuse surfaces. Then, of course, if you want to give a realistic effect rendering diffuse surfaces, which is most of the surfaces we have around, ray tracing is not the way to go. You need another method. This another method is called radiosity. The radiosity approach is an approach which starts from assumptions which are completely different. We do not take into account the geometry of the problem anymore. The idea on which radiosity based itself is borrowed from thermodynamics, and it's based on the exchange of energy. Radiosity is actually the rate of exchange of heat energy across a surface. That's the original definition of it. The idea is to subdivide your scene into small areas which are called patches. See? Each patch will emit a quantity of light and receive a quantity of light. The balance of emitted and received energy is the radiosity factor of that patch. For each value of radiosity, we associate a color. In this way, we assign a color for each patch. So every patch gets colored according to the rate of energy it exchanges. You can see that in this way, we don't take into consideration anymore if the object is diffuse or specular or whatever. We just calculate the energy that part of object gives and the energy that part of object takes. And then we convert the value of energy into a color. And in this way, we color the scene. That's the approach of radiosity. Of course, you have to take into account every possible pairing combination between each patch. And of course, the rate of exchange energy depends from the distance between the two patches you are considering and from the mutual orientation. That is, two patches exchange a lot more energy if they are completely parallel one against the other, like this, and then exchange a lot less of energy if one is orthogonal in respect to the other, like this. Right? So there is a lot to consider according to the geometry of the problem. Okay, so we will talk about ray tracing and radiosity in this term, and this is what basically ray tracing and radiosity mean. Then there is another thing that we can see, which is texture mapping. Texture mapping is widely used in computer graphics, and the technique allows you to convey a much better sense of realism than just the mesh. The mesh, only by itself, is actually a hollow surface. But you can hardly convey a sense of realism for complex objects, like, for example, consider this fire. Would you say that this is a fire? Not really. But when you put a bitmap image of a fire over this geometry, and you shade everything with color, then you get a good representation, a good 3D representation of it. So the idea is to enhance the appearance of a solid model of a 3D surface by mapping to each vertex, by mapping into each polygon, the pixel of a raster image. This is why it's called texture mapping, because I'm going to map which specific pixel of a texture image goes into which specific 3D vertex of a vertex model. So there are specific equations about this. There are specific mapping algorithms between the bidimensional space of the texture and the three-dimensional space of the model. And, well, there's literature about it, of course. So, and that's it. That's all. It's a complete different branch and group of algorithms about mapping textures. Okay, then. So, this I have shown you are some of the basic concepts we will see in these lectures. But in order to be able to understand all these topics and treat them in a scientific way, we need to brush up a little bit our geometry. So what we are going to do during the rest of this lecture is to go quickly to some geometrical knowledge that you should have, but don't worry if you don't remember it anymore, because we are going to brush it up together in the next hour and a half. So I would say for the moment, let's take a 10 minutes break, and when we start again, reviewing up our geometry. Sì. Sì. Sì.
Cioè? La profondità di campo, diciamo, a fuoco. Non ho ben capito come si definisce di preciso.
No, quello lì, la profondità è quella della tua lente. La tua lente c'ha una profondità di campo che determina quella del field of view. Tant'è che la lente è identificata da una distanza che è una distanza lineare, sì. Che dice che il campo che tu riprendi, che sì. Ok, allora chiamiamola distanza. In italiano si chiama distanza focale quella della lente, cioè 50 mm di distanza focale. Ok, grazie. Okay, let's start again. Okay, let's review a little bit. Let's review a little bit how we use hello. Hello. Let's review a little bit how we use vectors in computer graphics. As I said, the basic building block for everything is the vertex. The vertex itself can be represented with a vector by using its coordinates x, y, z. These can be easily put inside a vector, where x is the first component of the vector, y the second component, z the third component. However, for a reason that we will soon see, computer graphics tends to use homogeneous coordinates. In homogeneous coordinates, every point is, in fact, constituted of 4 coordinates. X, Y, Z, and W, being the last coordinate, the homogeneous coordinate. The homogeneous coordinate is very useful in computer graphics because it immediately gives you the notion if a specific vector is used to indicate a point or to indicate a vector. Well, a direction. I'm sorry. Why is this important? Because, as you know, you might end up, well, let's write it down and it will be clearer. Everything starts from a reference coordination system in 3D, and you have a vertex. Let's call this vertex P. We will soon see why, but this P, being a point, can be represented with its coordinates, x, y, and z. In CG, usually this is considered not enough. Why? Because the characters, well, the objects that we are going to handle are not only vectors, but most of the time are, well, vectors for coordinates, but most of the time are also vectors meaning directions. So maybe we have planes, and for that plane we have a normal vector to that plane, m. So sometimes we use a vector because we are interested in the position of one point. Sometimes we use a vector not because we use that vector to represent a point, but because we use that vector to represent a direction. You see? So we have a difficulty here already. We just started and we already have something strange. That we use the vector either to represent a position or to represent a direction. For example, if I want to represent this direction over here, this could be the direction x. That could be easily represented like this, 1, 0, 0. Right? That would be the direction x as a vector. Do you agree? So, but if I wanted to name a point, let's call it q, then I could say the point q is 1, 0, 0, because it's 1 in x, 0 in y, 0 in z. Right? But what I want to mean, you see the vectors are the same, but what I want to mean with them is extremely different. With one, I'm thinking about a direction, a vector which gives me the direction of the x-axis. With this one, I'm talking about a point which has a position in space. This is why one of the many useful uses of the fourth coordinate is to discriminate if this vector is indicating a point or it is indicating a direction. So the first general rule that you have to write on your skull here is the fourth coordinate for a vector representing a point is always 1. So every time we will be handling a vector which is representing a point in space, it will be the x-coordinate of the point, the y-coordinate, z-coordinate, and the scalar 1 over here. That's a point. Well, since we have decided this, that 1 in the fourth coordinate represents a point in space, then it's easy to understand what is the fourth coordinate which represents a direction in space. I'm explaining this to you so you can easily remember and never get wrong with this. So imagine that I have a point P, then that I have a point Q. Okay? Then I can have, these are 2 points, so it will be P, A, B, C, 1, and Q, that will be X, Y, Z, 1. So those are 2 points. But then I also want to represent a direction. So, for example, I want to represent this vector, which is P minus Q. This is the vector. So P minus Q, it will be my vector D for direction. You see, is represented by A, B, C, 1 minus X, Y, Z, 1. Right? So it will have A min X, B min Y, C minus Z, 0. Right? So which tells me that every time I see a vector whose fourth coordinate is 0, that vector is representing a direction, not a point. So this vector is actually a vector like this, P minus Q, has a difference between 2 points, is representing a direction, and its fourth coordinate is 0. So first rule, tattoo it on your skull. Fourth coordinate has a lot of meaning. Fourth coordinate 1, we are dealing with a point. Every time we're dealing with direction, fourth coordinate is 0. So that's the first thing, practical thing that we have to remember. So let's get back to the slides. That's easy. And here, RGB. So this is written here. Okay? Okay, we will do this very rapidly because I gather that you know your vectors more or less already, so you shouldn't. I'm expecting that you are not learning this kind of geometry for the first time here. So every vector has a component, so we said x, y, z, 0. And a few methodology, notation. I will write every vector with a bold character. So in my slides, every time you see a letter in bold, it means that we are dealing with a vector. During the exam, it's very hard to write in bold and differentiate it from normal. So in written handwriting, we do not use this convention, but as I showed you right now, when I was dealing with vectors, I always put a little dash over to the letter in order to indicate that that element, that mathematical element is a vector. This is very important because in our calculation, we will use vectors and scalars. What is a scalar? A scalar is just one single number with no component. Well, a regular number, 3, is a scalar. Okay? Those scalar, when we want to assign it to a variable, so let's say that p equals to 3, that p is not written in bold, is not written with a dash on top. Why? Because it's not a vector, it's a scalar. Okay, so it has no components. If I want to indicate one single component of a vector, then that single component of a vector is a scalar. And it's written with a subscript, like this. V with 1, V with 2, or V with X, V with Y, V with Z. These, of course, are scalars, so they're not written in bold, and they have no dash on top of them, because they are the scalars which are the components of the vector. How do we write a vector? We use this rule in CG, or at least in this CG course. Every time we consider a vector and we use this vector to represent a point or a direction, we always write it as a column, always like this. If you, for graphical reason or space reason or whatever, you need to write it in a row like this, then use the transpose. We always use points and direction as columns. In this way, we always stick to this rule, and we will always go with no problems when we will be performing transformation with the matrices, etc., etc. So we will always have points and directions as columns. Transformations as matrices, and all the operation will go fine with no mistakes. Why? We can write direction and vectors and points also as vectors. Okay? Where does this, confusion, if you want to say like this, from where does it start? Well, it starts from the fact that the coordinates of a point actually refer to a reference system. A reference system which is actually a set of 3 orthogonal, linearly independent vectors. So when we're actually saying that point P is located in x, y, z, what we're actually saying is that we are forming a vector which is the linear combination between the basis over which we are expressing the coordinates and the coordinates themselves. So this is actually what we're saying, that our coordinates are v1, v2, v3, but these coordinates are such according to the base I am currently using. Oh, I'm sorry. The coordinates, of course, are alpha 1, alpha 2, alpha 3, and the base is over here, is v1, v2, v3. So we write for short that point A over here has this coordinate, alpha 1, alpha 2, alpha 3. But we bypass or omit the fact that these coordinates are actually valid only for this specific orthogonal, let's say orthonormal vector basis, which is forming the set of coordinates that I am using. So the full writing should be like this. This is my A vector representing the coordinate of the number, and this is actually the coordinate set. V1, V2, V3, which are the three vectors which are forming my reference. This is important because in computer graphics, several times, we need to do transformations from one coordinate system to another or a different coordinate system. Because of projection, because of normalization, there are several reasons that we will see. So, sometimes when you express a set of coordinates, we do also need to say in relation to which coordinate system we are expressing these coordinates. And this is the way. Oh, and I want to introduce you to your new friend, the pencil. This is the first time that we meet the friend. So, welcome back also this year, dear pencil. Every time you meet a slide with a pencil, it means that there is an exercise for you to do, and which is an important one. So don't ignore the pencil. So every time you meet the pencil, stop, take your time, and perform the exercises or consider the hints that the pencil is suggesting you. These are important to prepare in an optimal way your exam. Skip one pencil, that's already 2 or 3, 4 points that you're losing in your grading. Do all the pencils, you're a good candidate for your 30 with kiss on the forehead. Okay, so let's read briefly the pencil for these slides. So it's important that the rule that you're using for writing vectors. It's because often we need to multiply points in the vectors by other matrices or to perform projection. So we keep it fixed in its representation as a row. As a general rule, all vectors that represent a point of direction are written as columns. And if you need to write them as rows, indicate them as transposed. So this is a very weak pencil. I mean, there's nothing for you to do. It's just a thing to remember. But it's the first pencil of the course, so it's a very gentle one. But towards the end, the pencils are very difficult. So let's start with a weak one, and the funny one will come. So first thing you have to understand here is remember fourth coordinates, either 1 or 0. So difference between position and direction. And every time you write a vector, write it as a column, and you will not have any problem in the following. Just to review quickly, what you can do with vectors, well, of course, you can multiply a scalar by a vector. That's the multiplication, scalar by vector. How do I sum two vectors? You should know that. But just in case, it is like this. You sum every component. So the first vector is P1, P2, P3. The second vector is Q1, Q2, Q3. The resulting vector is P1 plus Q1, P2 plus Q2, P3 plus Q3. Okay. Note that I couldn't write it in column because I haven't space in here. So I didn't forget to put transpose here because I'm always thinking about them as columns. Right? Sum of vector is commutative. What does it mean? It means that P plus Q is Q plus P. Multiplication of scalar and vector is associative. So this one equals this one, and this one equals this one. So this is feasible. What is the length or magnitude or norm of a vector? We indicate the norm by putting the vector between straight lines or pipes, if you wish. So the letter of the vector is in bold, and you have two pipes around it to tell that I am now considering the norm of that vector. What is the norm? The norm is a scalar which represents the length of that vector. How do you calculate the length of a three-component vector? By squaring each one of the components, summing of the squares, and then calculating the square roots of the sum of the squares. You should remember that. So that's important because it gives me the length or norm of that vector. Second thing is when you want to obtain a directional vector from 2 points, I showed it to you already, but the convention is that if you want to take the direction that goes from P to Q, you have to indicate it as Q minus P, and this is the direction. First one was the direction points, and this is the other one. This is easy to remember. If you consider the direction of this vector, for example, Q and P, it's like making Q minus the origin, so the direction is like this, P minus the origin, so the direction is like this. So in a similar fashion, if you want a direction like that, you have to do Q minus P. So that's also easy to remember if you consider how you make the direction starting from the origin. Normalization. What is normalization? Usually then, you can take a vector as a direction. You can calculate the norm of it. Usually the norm is a number which is different from the unit, from 1. Usually it is very useful to normalize directional vectors. Vectors which represent directions. Why is that? Because in many operations, I am using directional vector not because I am interested in how long they are, but just because I am interested which direction they have. However, since when I'm using them, I'm using multiplications, if I am multiplying things by a direction, by a vector direction, which not only gives me a direction, but also has a length, the effect that I have is that I force the direction by the multiplication of that direction. But if the direction I'm using is not a unit direction, I'm also increasing the length of the resulting vector, which might not be what I want. So to be sure that I am using only the direction of a vector when I'm performing vector multiplication, and I am not also multiplying the length of the vectors, usually it's a good practice to normalize all the vectors I want to use just because of their direction. So when I do not want to use the length, I normalize the vector and then I use the normalized vector to perform the multiplication. This is especially true when I'm only interested in the direction of the vector. So normalization is a procedure that allows me to obtain from one general vector another vector which has the same direction but the unit length. So this length is always 1. How do I do this? Very simple. I get the norm of that vector and then I divide that vector for its norm, like this. It's like multiplying it by inverse of its norm. By multiplying it like this, if I take again the norm of the normalized vector, this norm will be equal to 1, which is what I want. I want a vector in which I am interested only in the direction. So I don't want its length to get in my balls when I do multiplication, so I put its length to 1. So it will not interfere when I perform multiplications. Do you see? Be careful. First common mistake. Do not confuse a normal vector with a normalized vector. These are two different things. A normalized vector is a vector upon which you have performed normalization, which means that it could be a vector pointing in any direction, but with the property of measuring 1 in length. A normal vector tells you something different. It's a vector which is orthogonal to something else. And it could also be that this normal vector has a length which is not the unity. To have a normal vector with the length unity, you need a normalized vector. You see what I mean? I've lost you already? Normal means that it's orthogonal. Normalized means that it measures 1. They are not the same thing. If you want an orthogonal vector which measures 1, you need a normalized vector. Right? Or a normalized normal. That's normal, no? Okay. So these are all interesting things to remember. And here again, our friend the pencil. This time proposing something a little bit, it's like the games of Nintendo, you know. It starts very easy, then you have the next level, a little bit more difficult, then you go on, you go on, you go on, and the last level is completely crazy. So that's the same thing. So one step ahead, let's look at it together. You have a rendering software for each triangle, composing the polygonal mesh. You have to identify a vector of the outbound direction from the polygon, perpendicular to the plane of the triangle. This vector is the normal. I already calculated this normal. I don't tell you yet how do I calculate it. I will tell you later. This is the normal. See? 12, 0, minus 12. This is a normal. But this is not normalized. So I'm asking you, normalize this normal. Okay, you think of it, sit on the water closet for a little bit, perform a calculation. This is its norm, and this is the normalized vector for the normal. Look at this. This is something I require you to do, which is every time you perform a division, be sure to rationalize your results. To perform this count, you have to divide the first component by the norm, the second component by the norm, the third component by the norm. So the result should be 12 divided by 12 in the square of 2. You follow me? But this is not good, because this is not a rational result, because you have a square at the denominator. I want you to put all the squares at the denominator. So what you have to do, perform another multiplication of square 2 in the numerator and in the denominator. This doesn't change your result, but has the nice effect of reorder your result. This is the correct one that I want to see. Square of 2 over 2. Okay, this is standard algebra. You should be accustomed to it, right? Can you follow me? Right. This is not rocket science, right? Okay, good. Let's make one little step ahead. And let's meet again our friend, the dot product or scalar product. First of all, I want to make clear this thing. Why is this baby here called scalar product? Because the result of this operation is a scalar. That is one single number. I do not want to see on the exam a scalar product by two vectors and the result is another vector. There is something wrong with that. It's not a scalar problem. The scalar product between two vectors is a scalar, not a vector. So if you have a vector resulting from a scalar product, oops, there's something wrong in your ideas, okay? So scalar product, result is a scalar. What is the definition of a scalar product? Well, the scalar product between two vectors p and q is the multiplication of the mutual components. So px qx plus py qy plus pz qz. And of course, by multiplying and summing the components like this, what you get? One single number, which is k. That's good. But what does it mean? The scalar product has a very interesting and very important geometrical meaning, which derives from the following geometric property, that another definition of the scalar product is that the scalar between p and q, obtained like this, can also be obtained by taking the norm of p multiplied by the norm of q multiplied by the cosine of the angle between the two vectors p and q. This is a geometrical definition. It comes from trigonometry, where alpha is the angle between p and q. if we consider this definition, then we can understand what is the very useful geometrical meaning of the scalar product. First of all, it tells us if the two directions are mutually orthogonal, and if not, how much they are not orthogonal. Let's say like this. Well, let's start with the orthogonal. What's the cosine of 90 degrees? 0. Right. Yes. So if P and Q have an angle between them of 90 degrees, that is, if they are orthogonal, then their scalar product is 0. So if I perform a scalar product between two vectors and it comes out 0, it means that those two vectors are orthogonal, perpendicular. Right? If we put this one little step ahead, the sign of the scalar products tells me if the two vectors are pointing toward the same direction, he refers to the plane orthogonal to them, or to opposite directions. Look, you can see it here. These two vectors, P and Q, have a scalar product which have a positive sign, because of the sign of the cosine. The cosine going from 90 to 0 over here is positive, so you have a positive result here. If you go to the other way, then the cosine starts to be negative. So you have a negative sign. So it means that P with the scalar R have a negative sign, which means that the two vectors are pointing to opposite directions in relation to the orthogonal plane. This is very useful, because with just one operation, I can tell how two vectors are mutually oriented. Are they looking in the same direction? Are they going to the same direction? Or are they going to opposite direction? I just look at the sign of the scalar product. That's good. That's the first weapon in our weaponry, in our stock. Example. This is again our friend the pencil. Give me an example, a practical example of why the hell should I remember this thing. Well, for example, the dot product is used to determine if a polygon is facing towards the viewer or not, when a process of backface culling is taking place. What is the idea over here? Do you remember that sphere? Do you remember that day in September? Do you remember that sphere which was made all of triangles? If you can imagine it in your mind, it means that you have triangles put all around creating a sphere. You have to know that in computer graphics, every triangle has actually two sides, a front side and a back side. Well, it's like a jacket. You have the front side of the jacket, you open, and there is the inside of the jacket. The polygon is the same. It has a front side and it has a back side. How do I tell which is the front side and which is the back side of a polygon? I look at its normal. Do they disturb you? No more, no more, no more, no more. Well, we can close. Over here. By convention, we use the normal to tell which is the front side and which is the back side. The normal, which is going, a normal can only be going, well, oriented like this or like this. But the front side is the one in which the normal is outgoing. So this is the point of the normal. It's outgoing, so this is the front side, this is the back side. Okay? So the outgoing direction of the normal marks the front side of the polygon. The idea is, when I'm drawing shapes, meshes with polygons, the shape can take such a form in which actually I don't need all the polygons all the time in my scene. For example, when I draw a polygon mesh for a sphere, and I have a viewer in front of the sphere, actually the viewer sees only about a half of the polygons which is making up the sphere. Typically, which half? Typically, the half in which the front side of the polygons are facing the viewer. All the other sides of the polygons are behind the viewer. So the viewer does not see them. So my idea is, why should I spend the time and money to calculate, transform, shade, and rasterize a bunch of polygons that the viewer doesn't see? I cull them. I cut them away before making them enter in the pipeline, because anyhow, I don't need them. This is what I call backface culling. That is, I cut away all polygons which, rudely enough, are presenting their back at the viewer. Okay? So we cull away rude polygons that are presenting the back at their viewer. But how can I tell if a polygon is presenting the front face or the back face at the viewer? By using a scalar product between the viewing direction and the normal of each polygon. This is an example. If I consider the viewing direction like it's a direction, right? So we take a point on the polygon. We take a point on the viewer, which, by the way, is the center of projection. So we define the viewing direction as the difference between the center of projection and the point on the polygon. So V is COP minus P. Then we take the normal outgoing the polygon, which is marking the front side. If the front side has the same direction of the viewing direction, then the viewer is looking at the front side of the polygon. That's a good polygon. I keep it. If the viewing direction is opposite to the normal, which is outgoing to the front side, it means that the polygon is putting his back at the viewer. That's a rude polygon. I cull it away. Okay? How do I know that? I make the scalar product between N and V for each polygon. When N and V is good, that it is greater than 0, I keep it. That polygon is facing the front side. Well, that polygon is facing the viewer. If it is negative, that's not a good polygon. It's facing the back. So I cull it. Is it clear? That's very handy because for every mesh, I always have the vertex list and the normal list. So the only thing that I have to do is compute all the V's for each one of the vertex, scalar it for each one of the normals, and very quickly switching on and off the polygons that I don't need. Then the surviving polygons can be fed to the rest of the pipeline for shading and rasterization. And I save half of the work. Well, I do some extra work because I have to do this operation of backface culling, which is something more. But then there are 6 or 7 operations more downstream in the pipeline. And with this more operation, I do it on half of the polygons. So it might be worth it in terms of performance. Okay? It's hard to say because it depends how you're implementing your engine. But it might be worth doing. Mind though, I'm not telling you that every time, every engine, in every situation has to do backface culling. This depends. For example, in the case of the sphere, Bake Pascal, a sphere, makes sense because anyhow, you will not see the backward-oriented polygons. But in other cases, maybe it does not have any sense because you need also the polygons which are oriented with the back. It depends from your situation. It depends from your engine. It depends from your choice. This is a technique that is possible. Yes?
But for instance, the triangle have emit lights. You need to calculate gating, but how this cutting don't influence on other polygons here from it?
You said the triangle emits light. So you're talking about, well, I don't know, a part of a light source. Well, if you have such a concern, of course, you cannot cull this triangle if that triangle is important. So that is why I'm not saying that you should always apply backface culling. I'm not saying this. I'm saying that you can apply backface culling when it's needful, when it has a sense. So in my example of a sphere, it has a sense because anyhow, I don't need to cull the rest. I don't need to see the rest of the sphere. I can cull it. I don't want it. In your case, you're saying, well, but I have a light source, Okay, in that case, okay, don't apply backface culling. I mean, it's up to you. How could you implement this? Several ways. You can make an engine which is very simple. It backface culls everything. Or you can organize your meshes with a data structure, and on each data structure you can put a tag which says, this backface cull, yes. This backface cull, no. It depends from your implementation. Okay. My idea here is provide you with the notion, or with the idea, what is backface? I can't say that. What is backface culling? Okay. It's a technique that works like this. You can use it, you can't use it, it depends. Okay. But now you know how it works. It's very simple. And it's based on a scalar product. And pencil again. This time is a little bit more difficult. Consider a triangle belonging to a mesh with a normal vector such as n is 2, 1, 2 in non-normalized form, and a non-normalized direction of viewing, -2, 0, 4. Evaluate if the viewer is looking at the front side of the polygon. So I keep it up to you, but it's rather easy. Okay? You can perform your calculation. In this case, even if you are working with direction, because you're working with v and n, which are both directions, so you are not actually concerned what is the norm of these vectors. The distance here, it is of no concern. Do you see? I'm just using the direction. So in this case, actually, I'm not concerned in normalize the vectors because I'm not using the information length in that moment. I'm only interested in the sign, and the sign depends on the direction. So I don't bother normalize here. I'm just interested in the sign. But if the length or the distance is of consideration, then I have to stop a little bit to consider, do I need to normalize the vector? If so, I have to remember to normalize it. In this case, it's not necessary. Because anyhow, I just need the sign. So even if it is 4 or even if it is 1, it doesn't matter. I'm looking if it is greater than 0, equal to 0, or lesser than 0. Okay, let's forge ahead. There is another thing that we have to review or to learn, if you don't know it, is how we calculate vector components. Every vector has a parallel component and a perpendicular component. Because you know that actually, well, what's quicker? Probably this one. Sorry, I'm looking for the pencil. This is the vector, right? Over here. This vector can be seen as the sum of this vector and of this vector over here. Do you agree? Right. This is why these are called the components, because you can sum them together to obtain a resulting vector. This part over here is the parallel component. And this part over here is the perpendicular component. By convention, this is actually, I don't know if you find it in many books, but in this course I, invented this notation. That if you want to take the parallel component of P according to the Q direction, that is this vector over here, let's say the parallel projection of P according to Q, P on Q, then you write P pipe Q. P pipe Q is this vector over here. That is the parallel component of P over Q. How do I calculate it? From trigonometry, we know that this side over here is actually the length of this side multiplied by the cosine of the angle. This is trigonometry. So this is the hypotenuse multiplied by cosine of alpha. So, the norm, that's a scalar of course, the norm of P pipe Q equals to the norm of P multiplied by the cosine of alpha. But if you remember the definition of the scalar product, which is the scalar product P scalar Q is norm of P multiplied by norm of Q multiplied by cosine alpha, this is the same thing as writing scalar product divided by the norm of Q. So the scalar product divided by the norm of Q gives you P pipe Q. Okay? It's not very difficult. Well, it takes to look at it a little bit, but it's not difficult. This is a little bit more complicated because what do we have over here? Do we have a vector or do we have a scalar? Huh? Oh. Because this is a scalar. This is a scalar. It's a division between two scalars. Do you see? Remember, the result of a scalar product is a scalar. That's why it's called a scalar product. And this is the norm of a vector, which is a scalar. So it's a scalar over a scalar. So this is a number. This number, what does it tell us? It tells us the length of this vector. What we're missing here? We are missing the direction of this vector. This is why we need more information. The direction of this vector is actually the direction of Q. Right? So we know the direction because we know Q. But what is the problem? That Q inside itself not only has the direction what we need, that is the direction of Q, but it also has its length, because Q is longer than P pipe Q. So what we have to do is to normalize Q to obtain a vector which has unit length. This vector with unit length is very cute because we can use it in a multiplication to add a direction to a scalar without altering the length of p pipe q. You see? If we made a multiplication of p pipe q by q, we would obtain a vector. This vector would have the right direction, which is q. But its length would be wrong. It will be something longer, because the norm would be the result of the multiplication of the norm of q by the norm of p pipe q. Do you follow? To avoid this, we have to multiply p by q by a vector which has the same direction of q, but unit length. So the result will be a vector with the direction of q, which is what I want, and with the length, which is the scalar value p pipe q. So this is what we do. P pipe q as a vector, you see, is the norm of p pipe q multiplied by a normalized vector over q. We make a little bit of manipulation. This we already have said that it is p scalar q over norm of q, which is a scalar, multiplied by the normalized q. By the normalized q is the vector q over its norm. So this is the final result. And this is the complete vector with norm and direction of the parallel components. How is it? You think it's difficult? No, it's not. Wait until... Did you have the slides printed? Did you print the slides? No? So you don't know what is expecting, what you should expect. Huh? Okay, this is the parallel component. Let's calculate the perpendicular component, which is the other one. This is made with a trick. Okay. Look, the perpendicular component, I invented this symbol, which is the angle, okay, to remember that it is perpendicular. So, what we calculate here is the perpendicular projection of P in the perpendicular direction according to Q. So, it is this one over here. Perpendicular according to Q. What is the idea here? It's a trick. This is the perpendicular projection of P over Q. If we know already this one, this is the parallel projection of P over Q, right? But look, this one I already calculated. And this one, P, I know. So to calculate this one, what do? I take this one, and I subtract 1 time P. Then I subtract 1 time again P. And what I obtain is P perpendicular over Q. Evil, eh? That's real evil. So what we do is P, actually it's not like I said. Forget it. Let's do it again. It's not like I said. Because, I do it again. Sorry. This one is the sum of P by Q, let's reason like that, plus P like Q. This is this one. Okay? So if I know P already, to get P perpendicular to Q, I just take P and I subtract it from it P parallel Q. And this I get the result. That is something like this. P perpendicular Q is like having P minus P parallel Q. This is clear. This is how it should be. So that's the trick. And this is how it is done. P minus P parallel Q, but P parallel Q is P scalar Q over the norm of Q multiplied by the normalized Q. Subtract all this to P, reshuffle a little bit, and this is the result. Be patient. I want to do at least also the vector product, the right-hand rule, and calculate of the normal. Then we can stop. We are a little bit lagging behind. This is about the scalar products. But there is another useful friend that you should be aware of, which is the vector product. Well, the dot product is called dot product because you write it with a dot in between. The cross product, which is the vector product, is called cross product because you write it as an X in between the vectors. Why the vector product is called vector product? Any ideas? Because the result is a vector. You are a class of geniuses. So, since you are such geniuses, you will not repeat the mistakes of your ancestors. So you will remember that the scalar product gives you a scalar and the vector product gives you a vector. Why the vector product is useful? Because this is a very useful way to calculate a normal to two vectors. And this is actually the way we will use to extrapolate the normals to our polygons. And I will show you how. Well, first of all, the definition of the vector product. If you take P vector product Q, the vector product is blah 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 blah. Why do I say like this? Because this is the definition. But even I don't use this definition to calculate the vector product. What I use when I need to do when I need to calculate by hand a vector product, which is actually rare because we use calculators. But I use the 3×3 matrix. Do you know this, maybe? I use the trick of the pseudo-determinant over this pseudo-matrix. Do you know how to use it? How many of you remember? Don't be shy. Only this. What is it? I remember, but I'm not sure. Okay, less than half of you remembers. The idea is this. No, it's interesting to know because I would like a feeling to know if this review is useful or it's a complete waste of time. But I get the impression that it's useful, right? Yes. Okay, I'm happy. So, you build this matrix, which is a fake matrix. It's just something for you to work on to quickly calculate the cross product. The only thing that this method requires that you have to remember how to calculate the determinant of a 2×2 matrix. Do you remember that? Yes, right. Okay, the idea is that you put ijk on the top row, then you put the components of the two vectors of which you want to calculate the cross product. So you put px, py, pz on the second line, QX, QI, QZ on the third line. Now, set. Now you're ready to go. Then, second rule, I is positive, J is negative, K is positive. So you start from positive and you do positive, negative, positive. Okay? Then you start like this. You're starting with I is positive. You prune out, that is, you take away the row and the column belonging to I. So you don't consider this. Look. I'm doing it again. This time. So, now you're fixing yourself on I. You take away the first column and the first row. And, as you can see, you form a pseudo-submatrix of which you calculate its determinant. How do I calculate the determinant? I make the product of the first diagonal minus the product of the second diagonal, like this. So it's PYQZ minus PZQY. Fine. Then, how do I clear this shit? Right. Now you are to the second, that's J. J is negative, so that is why I put here minus J. With J, I prune out the first row and the second column. Now you see that my matrix is actually composed of these two parts over here, and I calculate the determinant like this. Px multiplies Qz minus Pz multiplies Qx over here. Fine. Then third step, I didn't finish. Clear out. Where is it? Over here. I'm focusing on K, pruning out the first row, pruning out the last column. I calculate the determinant over this. That means, well, K of course is positive, so it's plus K and PXQY minus PYQX. Right. As you can see, if you put the signs, you have three vectors. The first component, I, PYQZ minus PZQI. You see? This is the first component of your vector. This is the second component of your vector, which is PZQX minus PXQZ. And this is the third component, PXQY minus PIQX. Now you have another problem. So these are the components, the numbers you have to put. But what is the direction resulting from this vector product? To know the direction, you have to use the right-hand rule. What is the right-hand rule? You use your right hand. You take your index finger. Well, let's say that you're making P scalar Q, right? You put your index finger, and you put it along P. Then you take your middle finger and you put it over Q. The thumb is giving you the direction of the vector you have calculated. Okay? So the thumb is your result. You have to be careful that your index is P and your middle finger is Q. So this is the first, this is the second. The result is the thumb. The fact that you use the right-hand rule gives you a hint of the fact that if you reverse Q with P, then you are obliged to turn your hand. Turning your hand, the direction of your resulting vector reverses. This is called that you cannot break your wrist. Okay, you cannot break your wrist to make it work, because the cross product has a property which is called anti-commutativity. If you switch the terms, then your results get the inverse direction, the opposite direction. So when you calculate the cross product, you calculate the three components and you obtain the direction using the right-hand rule. Remember that your index is P, your middle finger is Q, and your result is the thumb. So the cross product is very good because it allows us to calculate the normal. You see, this is P, this is Q. It's like these are the two sides of my triangle. And this is the normal to the triangle. So the result of a cross product gives me the normal. Another geometrical meaning of the X product is that half of the norm of the vector product is the area of that triangle. That could be useful to understand in the triangle if the polygon is big or small, which could be useful in some polygon-based processing. Okay, so you have another pencil that you can make at home. I gave you three vertices, A, B, and C, and you have a triangle over here. Calculate the normal to this triangle. So, B minus A, C minus A, vector product, this is the result. You do this pencil by yourself at home. Look, in this vector I used only three coordinates. Which is the fourth coordinate of these vectors? I don't hear you. 1, that's correct. Why? Because it's a point and not a direction. Good. And what would be the fourth coordinates of this vector n? 0. Because that's the normal, which is a direction. All right. All right. Well, we still have a lot of work to do. I'm sorry that it turns out that we are already a little bit late, but don't worry, we will catch up. Well, thank you for your attention, and see you again, I think, I don't know, a couple of weeks. If you have problems, just write me on the cyberspace. Bye-bye. Perché non c'è lezione? Vediamo. C'è il calendario. E quindi? Vediamo. È sul calendario comunque, eh? Noi facciamo quello che c'è scritto sul calendario. Che palla! Da svidania! Da svidania! Eh sì, non c'è settimana prossima. C'è il 31 e noi ci rivediamo il 7 novembre. Devo muovermi. Come mai non c'è? Perché ci sono le lauree.
Infatti non è sul calendario, però noi abbiamo un altro corso la mattina
ormai è così, il mio calendario è già tutto incastrato. Vabbè, intanto c'è tempo, noi queste sono le giornate. Tanto arriviamo al 16 gennaio, le giornate sono queste. Le ore di lezione sono quelle, più di così poi non me le paga, quindi io più di così non ne faccio. Questo è poco ma sicuro. Va bene, no, il 31 è la prossima con la Canu e il 7 novembre è la prossima con me. Ok. Beh, intanto fatevi un po' di esercizi, no? Ok. Dica.
Ho fatto ruotare un semplice quadrato colorato magari non è utilizzato per proteggere con Eclipse, quindi non so, magari deve essere utilizzato. Mi sembra strano.
Tutto è possibile. Se lei fa, scrive un semplice programma C, e nel semplice programma C scrive while true, graffa, e lo fa andare, le perde il 100% della CPU.
Ah, quindi è perché è il ciclo, è il loop.
Certo.
Ah, ok.
Se fa while true, aperta, thread sleep 100, e quindi fa uno sleep ad ogni ciclo, le prende il 2% della CPU. C'è una roba troppo stretta sotto, lui continua ad andare in ciclo.
Mi sembra strano, se è una semplice rotazione comunque.
Il programma è molto stretto. Sì.
I would like to ask you about the username in this course without meditate.
Yes. What?
I am for the first time and there is a username and password. What type of username?
You decide your own.
Particular username password?
It should be, but if you don't know, you can make your own username and password. You can do there, subscribe, and you put I don't know, John Lennon, username John Lennon, password Beatles, and there you go.
To email, yes, there is a password.
Yes, it's okay. You can do like this, but normally it should be your ID number, and I don't know what is your password. Probably it's given to you already. I don't know actually. For one, I used the John Lennon option. Well, I use my nickname and that's it. And after that, you have to subscribe to the page of the course. All right? Okay. Bye-bye.